So frames and machines are a very difficult part of statics. And in this video we're going to talk about we're going to go right to the hardest type of problem and just show you why these problems are so hard. We're going to zero in on the exact reason why and what you want to watch out for when you're doing these frames and machines. But let's just start out with some basic information. So frames and machines. Frames are things like this. This structure is not supposed to be moving. It's a frame. So pretty simple. Machines are things that are supposed to be moving. These two things are machines because what they're supposed to do is they're supposed to have moving parts. You know, this guy's supposed to clamp his fingers, and that's supposed to take this whole thing and move it this way, and you know, we'll have motion here as well. But for the purpose of solving problems, it doesn't matter, because even if things are moving, we're assuming they're moving with constant velocity, such that the acceleration is 0, and therefore this whole side of Newton's second law is 0. And of course, same thing for some of the moments. The angular acceleration is 0. So in terms of problem solving, nothing different. We apply the same rules and equations that we've done in the past. So another thing that's different about frames and machines is that some of our members in our system are not two-force members. Remember, a two-force member is going to be something like this. So for this member AD, there's really only 2 points of contact. There's this point of contact here where the pin joint A inserts into, and then we have this second point of contact here where the pin at D inserts into. So there's only 2 touch points, 2 points of contact, and because of that there's only 2 forces, and because of that we know that these 2 forces must be along the same line of action, which in turn means essentially we know the direction of these 2 forces. And lastly, because we know that, each one of these forces is just one unknown here. One total unknown, and we might call it, force AD. But for our non-two force members, like EDC for instance, all we can say about this is that the pin support at E will put one force on EDC, and this one force will have 2 components, which we'll call EX and EY. And same thing with the pin C. The pin C will also put one force, but all we can say is that this one force will have 2 components, maybe CY and CX. So in frames and machines problems, we're going to have many non-two-force members like this. Okay, so just some basic intro level stuff, but now let's start getting into why frames and machines are tough. And this is a bit of a long argument, so bear with me on this. So let's zoom in to this joint D and see what's happening here. So this member AD and this member EDC are really connected by this pin, this cylindrical pin here that is inserted right into these holes. So we can imagine that I line the holes like this, and this pin grows right in, like that. Seeing this in your head is the key to dodging the tricky parts of frames and machines. You've got to be able to break this down like this. So let's just pretend for the moment that we know that our green member AD is in compression, maybe with the magnitude of 70 newtons. Alright, So we got to go through Newton's third law here. What is creating this 70 Newton force? This guy is. Remember, from our visualization of how the green and the purple member and the pin are all kind of connected to each other, we know that this guy is touching this guy. Not this guy. This guy is not directly touching this guy. So it's this pin that puts this 70 Newton force on our green member. And therefore, if we use our Newton's third law statement, we know that in turn, the green member must put that same force, that same 70 Newton force, just in the opposite direction on our pin D. Okay. Well, looking at our pin D, we know that there's only two things touching pin D. There's the green member, which we already got, that's the 70 Newton, and there's the purple member here. Well, for there to be equilibrium, we know that this purple member must put an upwards diagonal force of 70 newtons on our pin at D as well. So this is the force from A, D, that's 70 going down diagonal. And here's our force from EDC, going up diagonal. Well, we can do Newton's third law one more time. If EDC is putting this 70 on this pin, let's reverse that. That means this pin is putting this 70 on our purple member EDC. So what we have here is a perfect transition of force, 70, 70 to this 70. No force was lost or transmitted elsewhere because essentially there's only the interaction in between these two green and purple members. So here's the important takeaway from this. Because we only have really two things happening here, we only have the green member and the purple member. Because we really only have two things happening, I can sort of neglect the pin. I don't really need to go through these extra Newton's third law steps to figure out the effect on our purple member. So, rebooting this conversation here, I can sort of pretend that the green member and the purple member are in contact directly, and I don't need to really think about that pin D. I can say that, okay, what is putting this 70 Newton force on the green member? The purple member. So therefore, Newton's third law says that the green member, therefore, must be putting that same 70 just downwards diagonal on the purple member. So I arrived at the same final result as I did before, but I didn't have to go through those extra steps of going through the pin. So, hopefully this makes sense because this is a huge thing to watch out for. If I only have really two things interacting at a particular pin or junction or an intersection, smooth sailing. Don't need to do anything crazy. I don't really need to really break it down and do a free body diagram on this pin D. But you'll notice that this isn't the case everywhere. Check this out right here. What we have is a pin C that has three things acting on it. It has this 5 kilonewton external force acting on it. We have the point of contact between our purple member, so that's going to be some sort of force with two components. So I'll just write a X and a Y component. And we also have a member up top that's connected, and that's going to be sort of a third effect, a third force, which brings two additional components. So here, this is where it gets dangerous, and this is why frames and machines problems are very tricky. You've really got to break it down at these particular situations and run it through that pin to figure out exactly what's going on. force is not being transmitted equally here. This 5 kilonewton force, some of it will be balanced by our blue member, that would be member BC, and the rest of it must be balanced by the purple member, EDC. And you've really got to do the free body diagram, some forces X, some forces Y analysis to figure out, you know, how that conversation ends. So this is the essence of frames and machines problems and what you have to watch out for. So let me just write that down for you. So another one of these more than two things scenario is going to be here at pin A. And you may be wondering, wait a second, we just have a pin and we have two members. Well, really, isn't that this situation? Well, this pin at A isn't just a pin, isn't just like a passive pin that's just sitting there to transmit force. This is a support reaction here. So it is actively creating forces that are helping keep our system in equilibrium. So this is one of these situations. If you're ever unsure though, you can always break it down. It never hurts to break things down completely, just so you're sure that you're not missing anything. Okay, so what we're going to do is we're going to change the question. Instead of determine the components of reaction at E, we're going to determine the components of the reaction at A. And you'll see more of what I'm talking about. So what we're going to do first is we're going to do a free body diagram of this entire system. We're just going to treat this entire thing as just one big blob. All of our members here are internal to this big blob. Okay, so what are the things coming from the outside? What are the things external, the external forces to this blob? Well, one thing that we know is touching it is going to be this pin support A. And we know a pin support will put one force, which has an unknown direction, so we just say, you know, two reactions. But I'm going to be very careful how I label this, and you'll see why I'm doing what I'm doing. This is the force of pin A on the system in the X direction. Got that. And I'll assume the other component is going up. That's going to be A on the system in the Y direction. And again, just a sneak peek here, the reason I'm saying this, the reason I'm not just saying AX and AY, is that as we'll see later, we're going to zoom in here and we're going to realize that this pin at A, those forces that it's creating are touching these two members right here. So this force, which is really the answer to our question here, this force is going to be split between these two, and it's one of these weird situations that we're really going to have to break down. So that's why I'm making sure I'm knowing that this force here is really acting on both these things, not any one individually. Another thing external to our system is going to be that pin at E down there. And that pin at E really is only touching this member EDC, so I'm not going to have this confusing case. But again, if you wanted to say E on the system in the X and E on the system in the Y, like I did here, you can totally do that. But since I know that pin at E only acts on that member EDC, it's only touching EDC, I know nothing's going to try to trick me, it's just going to be easy. So I can just call it EX and EY. Okay, well we also have this triangular load right here. I'll skip the details on this just because that's not the focus of this lesson. If you work it out and do your steps like we've done before, that will equivocate to a 6 kilonewton force. And it's perfectly symmetrical, so it'll be right there at 1.5. And this 5 kilonewton force, that's also external to our system here, so 5 kN. Alright, so free body diagram's done. So I'm quickly going through my head and I'm thinking about some forces x equation, some forces y equation, some moments about some point equation, seeing which ones will be useful, which ones will get us answers immediately, and which ones won't. Some forces x and y have a lot of unknowns to deal with, so I'm going to stay away from that. But if we do a sum moments about this point right here, these two will cancel, this will cancel, and therefore I can find out EX. So that's useful, and we'll do that. So I won't really go through the sum moments equation too much in depth. You guys should be pretty good at it now. Just remember our dimension here is 2, and our dimension here is a 1.5 and another 1.5 to make a total of 3. And my counterclockwise is positive, so the moment that our EX is providing about A is going to be positive. So we'll solve this equation and we'll get a positive 12 kilonewtons. And remember that positive means that my assumption was correct. My assumption for EX was that it was going to the right, so that's good. I'm going to leave this picture as is. What you'll find is that, at least the way I do it, when I get a negative, I'm going to change my picture, and that will reflect a lot of other forces that depend on that main force. So just make sure, if you get a negative number, just change your picture to reflect what you've learned. So I'm also going to put 12 newtons on our picture, so we have that. Now, imagine I do a quick sum of the forces in the x. I only have 2 forces acting in the x here. I have this, and I have this. If this is acting to the right with 12, this is acting to the left with 12. Don't even have to write out the math there. I'm going to change my picture, though. What I'm learning is that the force from that pin support reaction A onto our entire system is actually going to be to the left with a magnitude of 12 kilonewtons. So this is half the battle done, actually, because these two things are what I want. The reaction at A, the effect that A has on our system. Now, if I do a sum forces in the y, I'm going to have these two unknowns right here, so that's not going to work. And even if I do another sum moments, like maybe a sum moments about this point, I'll have these same two unknowns in that equation as well. So it really stinks that these guys are on that same line of action. So we're going to have to move on to analyze another system and develop some more equations. Alright, so let's move on to analyzing member AB, and pay attention here because we're building up to the tricky part, the part that's going to trick many students when doing frames and machines problems. Alright, so what is touching AB? What forces are acting on it? Well, of course, we got that same distributed triangular force that equivocates to 6 kilonewtons acting at the midpoint. We also have this thing going on over here. Zooming in on that pin B, I know that it's going to be connecting AB to BC. So really this is it. This thing goes in together here and locks these two members together. Like so. Something like that. I don't have anything else going on. And if you're wondering, yeah, this triangular force is only acting on this member. It's not acting on the pin, like we looked at before. So the force from this guy will be transmitted perfectly to this guy, and therefore we can just pretend that this guy is touching this guy directly. And that's important because remember, BC is a two-force member. Only two things are physically touching it. The pin down here at C and the pin up here at B. Pin C and pin B. Only two things touching this member. Therefore, it's a two-force member, and therefore we know that that force is either going to be going like this in tension or the other way around in compression. A very useful fact for us to leverage. Remember, always look for those two-force members. I'm going to assume that BC is in compression. I'll call this force BC. I'll call this BC. So therefore, using Newton's third law here, we can say that this force, or that member BC, will push up with an intensity, a magnitude of BC. Just Newton's third law there. So lastly, the last thing acting on our member AB is the thing here. The effect that pin A has on our member AB. And this is where we have to be careful. It's not these guys. I won't do Newton's third law here. Remember, those guys are the force A puts on both AB and AD. It's the force that it puts on the entire system. What I need to write here is force that A puts on AB. And since this is a regular pin support, I know it's going to be an ABX, which I'll assume right, and an ABY, which I'll assume up. Alright, so now for the math. A simple sum moments about A will allow us to calculate the force activated in that two-force member. And they'll do that sum moments equation, and they'll get that the force here, BC, must equal 3 kilonewtons going up. So that's all well and good. We can do a quick sum forces in the Y. We only have the 6 going down, a 3 going up. So of course this guy here will need to be 3 to push up as well. And this is where everyone messes up, right here. What everyone will do is what they'll say is that, okay, they will have been calling this AX, and they will have been calling this, AY, and they will have been calling the other one AX. And they would have just figured out that AY is 3. And they would have been thinking, alright, I got AY. Oh, up here in my main system, free body diagram, I have AX. They would have just been calling this, AX and AY. And they would have thought they would have been done. 12 and 3 are the components of the reactions at A. But they're not correct there. Remember, these two things are the force of this pin at A just on this member only. But what we want, what the question's asking for, are these guys. The effect that pin A has on the entire system. So that's the tricky part about frames and machines problems. These junctions where these weird things happen, and you really, at these junctions, you've got to break it down. And let me just really illustrate that for you before we move on in this problem. Okay, so it's all about breaking things up. These two forces right here are the forces that pin A has on the entire system. Using Newton's third law, we can say that the entire system puts these two forces on A. 12 going to the right, and the system on A in the Y. Notice that this is just the Newton's third law turnaround of that force there. So these things all together, this is the force that the system puts on that pin A. Well, let's be a little more specific. What things are actually putting these forces on pin A? What two things or what things are touching pin A? Well, the only two things touching pin A are AD and AB. So we say that the force that AB puts on that pin support A, and the force that AD puts on that pin support A, these both things come together to create this. So again, it's that idea of force transmission. The force that pin A puts on the system, some of it's given to member AB, the other is given to member AD. As we can see, this, which is, Newton's third law turnaround in this, of that, and this right here, these are not equal. So be very careful. A lot of people see this and they think they've gotten that second half of the answer. They think that, all right, I got the 3, got the 12, so I'm good. No. Be very careful. So let's keep going through this frame and analyzing the different pins and joints and members, and you'll see how we eventually will solve for the components of the reaction at A. Alright, so now with our member AB, we can do some forces in the X. Other than this one, there are no forces in the X, so therefore this has to be 0. There's nothing to balance that force, so therefore it must be 0. Alright, so we analyzed AB. Well, let's go down to BC and see what's going on. Well, we know that BC is pushing up on AB with 3. So let's Newton third law that. AB is pushing down on BC with 3. BC is a 2-force member, therefore this has to be 3 as well. Now again, here comes one of those tricky things. And I'm actually going to be very careful about how I describe this. Since this is one of those dangerous moments, I'm going to make sure I say that this is the force from C onto BC. And that is what is equal to 3. So, I can't just neglect this pin at C. I really got to take it apart and analyze it. We know that C puts an upwards force on member BC. Newton's third law says that member BC must put that same force downwards on that joint C. Downwards with 3. And just to get the subscripts, this is the force that BC puts on C. And maybe I didn't mention this enough, but notice how, when I'm flipping these subscripts, I'm using that Newton's third law statement. But these 3 are the exact same number, just opposite direction. The force of C onto BC and the force of BC onto C. I was doing that a lot with what we were talking about over here, so hopefully you were able to follow that. Alright, well, we also got this 5 kilonewton force on our pin C, so I got to make sure I write that. Okay, but don't forget, I also have EDC touching this pin. EDC is not a 2-force member, so I know its force won't be as simple as this. So I'm going to say, okay, let's just say that EDC does this onto that pin C. I'm just going to make sure I get my subscripts. This is the force from EDC on C in the X, and the force from EDC on C in the Y. Well, simple sum forces X and Y here. This guy's going to have to be strong enough to take on this 3 and this 5. So he's going to have to be 8. And this guy has no one to balance him, so he must be a 0. Alright, so we navigated that one pretty successfully. So we'll analyze our member EDC next. Got to be very careful. This 5 kilonewton force acts only on the pin, as you can see from the picture, and it kind of gets tough there to see that, but you can see that that line is directed to the pin. So I'm not going to write this 5 here. That'd be a big no-no. I gotta use my whole Newton's third law again. EDC puts 8 up on pin C, therefore pin C puts 8 down on EDC. So 8 down from E onto EDC. And there's nothing in the X, so no need to worry about that. Now, AD comes into contact with EDC right here. But this is not too much to worry about here. No tricky business going on, no extra forces, so I don't really have to analyze that joint D. I can really just pretend AD is touching EDC directly. AD is a two-force member. It only has 2 touch points, here and here, so therefore I know the direction of its force. And I'm going to say that that force is going to be this way. I can do some quick trig to figure out this angle right here. My opposite is going to be this 2. My adjacent is going to be 1.5. So inverse tangent of 2 divided by 1.5. And that'll get us 53.1 degrees. And this whole green force here is the force from AD. Got that? Of course, my pin joint reaction E is acting here. But again, since I really only have 2 things, the force from this guy really just goes to him. So I can bring these guys over. These guys actually are acting directly on EDC. Whereas pin A is acting on both AB and AD. So that's why pin A was so complicated. But EDC isn't, or E isn't. So we're going to have an EX, and that's the 12, like we already know. And EY is unknown, and I assumed it going up in my main FBD, so I keep that assumption here. So everything's ready. I can just chug my math now. Some moments about E should allow us to get AD. Alright, so here's our some moments about E equation. And if we do that math, we can find AD as equaling a negative 20 kilonewtons. So I got a negative. That means my assumption was incorrect. My assumption is that AD is acting this way. I'm going to fix that on my picture right now. So it's actually acting this way. And I'm going to make sure I go to all my other pictures and change it up as well. But as it is, I don't have this AD force in any of my other FBDs, so I'm safe there. So AD is 20 kN. And I can do a quick sum all of my forces in the y direction to figure out EY. So here's my sum forces y equation, and if you crunch out that math, we'll actually get that EY is going to be a negative 8. So my assumption was wrong. My assumption was that EY was going up. Got to switch that. EY is going down, and is equal to 8. Got to reflect that across my work here. There it is right here. Got to make sure I reset. And I now know that it is equal to 8. Okay. So we can actually do a sum forces in the X too. But notice that we have no unknowns in the X. So this is a way for us to check our work. The sum of all these forces in the X direction better equal 0. If it doesn't, we know we've made a mistake. So let's run that check. So here's my sum forces in the X. Apologies, I think I just realized I circled this force as acting in the X, but it definitely doesn't. Yeah, my only 2 things are the 12 and the X component of that AD 20. Yeah, so luckily, when I carry out this math, I'm getting very, very close to 0, so I think that I am good. Alright, so we've really traversed through this entire frame here, And that's what frames and machines problems are really like. It's kind of like a truss, but more complicated. Not all the members are two force members, and then on top of that we got these very difficult junctions that we have to navigate around. So, looking back at our entire system free body diagram, notice that we could now use some of the forces in the Y to figure out that missing piece of the answer that we needed. If I add up my forces in the Y, I got a 6 going down, a 5 going down to make 11, an 8 going down to make 19, so I have 19 going down. This guy needs to be 19 going up for there to be force balance in the Y. So that'll be my other reaction. So the force from pin A on my system in the Y will equal 19, and it's in the positive Y direction. So these two are my answers. These two are the components of the reaction at A, the effect that A exerts on our system. And we can actually check this and verify that it is correct, kind of similar to how we did here. So let's do a free body diagram on that support reaction A. Just keep in mind Newton's third law here. A does these two things to our system. Therefore, our entire system is going to do these two things onto that pin joint A. Again, these two things are the forces from our system on A. Now, we know in actuality, the entire system isn't touching pin joint A. It's really just these two members right here. So, this force from our system onto A really comes from the force from member AB onto A and the force from member AD onto A. I mean, we can write each one of these as a vector. We know that the force that the system puts on A are going to be these two guys right here. A positive 12 in the I and a negative 19 in the J. Now, the force from AB onto A. Well, looking at our work we've done with member AB, we know that A does these things onto AB. Well, let's just switch that up using Newton's third law. AB will do the same things onto A, just equal and opposite. So a 0 in the I, of course, and a negative 3 in the J. Now, for the force that AD puts on pin support A, we haven't really discussed AD yet, but we can do that very quickly. Let's do Newton's third law right here. Newton's third law tells us that if this is AD, I'm going to have 20 going this way and 20 going this way. And Newton's third law again says that, hey, if pin support A puts this 20 on this guy, that means AD is going to put this 20 on A. So if we break that up into its vector components, we'll have a 20 cosine of 53.1. That's all in the positive x direction. And we'll have a 20 sine of 53.1. And all of that is going to be in the negative y direction. So if you carry out this vector addition with the component method, adding this x with this x will get you 12, and adding this y with this negative 3 will get you negative 19. Our check passes. So we know we're correct, and we know that these two force reactions are our answer. So, pretty crazy stuff. but I wanted to show you how hard these problems can get, and I wanted to highlight the essential skills for navigating these sorts of problems. Newton's third law, breaking up these pins when you have to at these dangerous situations, recognizing when you don't have to. But remember, you can play it safe and do it anyways, and you'll get the same thing. This problem that we've done right here is going to be like an exam problem. This is the top tier, hardest difficulty sort of problem right here. So you'll definitely want to get practice working out these sorts of problems. Most of the other problems in the book are a lot easier. But in the next couple of videos, we'll work through more problems like this just to get some more experience. Yeah, for sure, frames and machines, not easy stuff. It's trusses, but a lot harder. You still have to work through all your members and stuff, but yeah, a lot more pitfalls that you have to dodge. This way of breaking things up, this way of thinking, zooming in on a joint, breaking it apart, seeing where all the different pieces connect, this is an extremely important skill for civil and mechanical engineers. So just make sure you're noticing all these things because you're going to see it a lot in your later classes. Alright, hope that made sense. Please ask any questions you may have in the comments.